We are here at Master Squash Courts filming an experiment called the Physics of Squash. So we're going to be analyzing the ball movement as I hit the ball.
Okay, so obviously that shot hurt a lot, but now we need to figure out the physics behind why that shot hurt. So in order to do that, first we need to calculate kinetic energy. We need that by first figuring out what the mass of the ball is. We know that the mass of the squash ball is 0.024 kilograms, and now knowing that the fastest shot ever recorded is 78.23 meters per second, and knowing Dave obviously can't hit that great of a shot, we're going to estimate that the velocity of his shot was 32 meters per second. Now, using the kinetic energy equation we learned in class, which is the mass of the ball times the velocity of the shot squared, we find that the average kinetic energy for this shot was 12.28 joules. Now, a major assumption that we are making in these calculations is that this shot was hit in a vacuum and that no kinetic energy was lost due to the ball traveling in the air. So now, this doesn't necessarily describe why the shot hurt. In order to get a better understanding of that, we're going to calculate the energy density. The energy density is the energy of the shot divided by the area at which impact was made. The impact area takes the form of a circular welt. For the purposes of these calculations, we are going to assume that the radius of this circular area is 0.01 meters. Now, plugging that into the energy density equation, we find that the average energy density for this shot is 40,000 joules per meter squared. That is obviously a lot of energy per unit of area. Very similar to the energy density of a paintball, which we looked up to be 50,000 joules per meter squared. So this shot hurt only slightly less than getting hit by a paintball. Now, this is not the only factor that goes into determining whether the shot actually hurt me or not. Another factor that goes into it is the material at which the ball is made of. So now with our rearranged impulse equation, we see that a larger time interval for the impact will result in a smaller average force and less pain. Because the squash ball is made of rubber, when it hits you, it's going to have, on average, a larger time interval at which impact is made. So this will result in a smaller average force and, of course, less pain for me. This is being compared to whether the ball was made of solid material. If the ball is completely solid and it hits you, it's going to have a very small time interval for the collision and, of course, a larger average force and a lot more pain.
Okay, so we were talking about impulse with the context of the ball hitting Freeman. Now let's talk about impulse in terms of me actually hitting the ball. So as we know from our impulse equation, the change in momentum equals the average force exerted on an object times the time interval. From before, velocity equals 32 meters per second of the squash shot. Mass is 0.024 kilograms. And the typical range of a racket ball collision is from 0.005 seconds to 0.05 seconds. So if we rearrange our impulse equation, we solve that I'm going to have to exert an average of 15.3 newtons of force to accelerate the ball to about 32 meters per second. Now, 15.3 newtons of force, I mean, that's not much. That's a pretty significant amount. I mean, I'm going to hit the ball at 32 meters per second, and it's going to feel like a paintball when it hits Freeman. But let's talk about this squash ball collision in terms of something that's actually going to hurt or seriously injure Freeman, something like a bullet. So a bullet has a mass of about 0.0042 kilograms and a velocity of 762 meters per second. So a bullet is going to carry about 1,219 joules of energy in the air. That is a lot more than what we saw earlier with the only about 12.8 or 12.28 joules of energy with the squash ball. So how fast is the squash ball going to need to travel to carry this much kinetic energy in the air? Well, solving the kinetic energy using the mass of the squash ball, we find that the squash ball is going to have to travel about 319 meters per second. That's pretty fast. How hard am I going to have to hit the ball to get it to travel that fast? How much force am I going to have to exert? Well, this is just our impulse equation from before, assuming that I'm hitting the ball from rest up to speed of the 319 meters per second, and we get about 153 newtons. That's a whole factor of 10 greater than an average shot. That's probably physically impossible. I likely can't hit the ball that hard. Anyway, this is the physics of squash, and we hope you've enjoyed.